In the context of synthetic topological quantum matter, the Kitaev chain has garnered significant interest due to its potential in realizing non-local zero-energy Majorana Fermions at its edges. These quasi-particles are crucial for topological quantum computation. This paper proposes a new approach to detect these Majorana Zero Modes, MZMs, through their optical signatures in the absorption spectrum of a semiconductor nanowire. The proposed system consists of a hexagonal INP nanowire with an array of embedded in ASP quantum dots, placed in proximity to a p-wave superconductor and under an external magnetic field. The Hamiltonian of the system, H, includes terms for electron and hole hopping, pairing between adjacent conduction levels, and Coulomb attraction between electrons and holes. The Kitaev Hamiltonian, He, is a key component of H, describing the hopping and pairing of electrons in conduction band levels. The chemical potential is tuned to bring the chain to near half-filling in the absence of superconductivity. The paper discusses the Kitaev Hamiltonian in detail, highlighting its ability to support two MZMs localized on the ends of the chain when in the topological regime. This regime is centered on parameters increment equals t and micro equals 0. The authors employ an exact diagonalisation method for normal fermions, following Kitaev, and introduce a new set of fermions referred to as bond fermions. They demonstrate the usefulness of these bond fermions by matching energy spectra obtained through both normal and bond fermion bases. The rest of the paper utilizes the bond fermion basis for analysis. The theory presented here focuses on the interaction between photo-excited conduction electron-valence band-hole pairs and Majorana fermions in the Kitaev chain. This interaction leads to the formation of bound states that generate peaks in the absorption spectrum of the system. Among these peaks, there is a signature of MZM, which is the primary focus of this study. The authors aim to identify and predict the absorption spectrum of the semiconductor nanowire, with a particular emphasis on the optical signature of the MZM. The research paper discusses the application of exact diagonalisation and the use of bond fermions to solve the Kitaev Hamiltonian. It begins by introducing the exact diagonalisation method in the normal fermion basis, where the Hilbert space is spanned by electron configurations. The Kitaev Hamiltonian is then expressed in terms of Majorana fermions, which are used to define bond fermions. The Hamiltonian is rewritten in terms of bond fermions, shown pairing between Majoranas of different types in adjacent sites. The paper highlights the importance of the parity symmetry, which allows the Hilbert space to be broken into two decoupled subspaces of even and odd configurations. The energy spectrum of a chain of n equals 3 quantum dots is demonstrated in both the normal and bond fermion basis. The use of bond fermions is shown to diagonalize the Hamiltonian in the topological regime, resulting in a set of n-1 quasi-particles with energy 2t and one non-local quasi-particle with zero energy, known as the zero mode. The research paper explores the energy spectrum of the Kitaev chain, a topological superconductor, in both normal and bond basis. Figure 3 illustrates the energy spectra for increment equals t less than 0 and micro equals 0. Showcasing a doubly degenerate ground state, singly excited states, and doubly excited states. The bond fermion configurations are the eigenstates of the Kitaev Hamiltonian under these conditions. Table I summarizes the energy spectrum in terms of bond fermions, highlighting the configurations, labels, parity, and excitation energies. The paper then investigates the absorption spectrum of the chain and the optical signature of the Majorana Zero Mode, MZM, by studying the energy spectrum of the full Hamiltonian with one hole in the configuration space of bond fermions and one hole. The Hamiltonian is solved using exact diagonalisation, and the configurations are listed in Table 2 for n equals 3 dots. The whole Hamiltonian HH is a constant eta and mixes states with the same electronic configurations and different locations of the hole by hopping matrix element tau. The full Hamiltonian with one hole has a block structure, with each block being a 4x4 matrix. The interaction term hint mixes different bond fermion configurations, depending on the location of the hole. When the hole is not at the ends of the chain, hint mixes two non-zero bond fermions, and when it is at one of the ends, it mixes the zero mode with one of the non-zero ones. The energy spectrum of the electron hole system is presented in Figure 4, showing the branching into two groups of states, corresponding to bonding and anti-bonding pairs, mixed by the interaction V. The left panel illustrates the energy spectrum for a localized hole, tau equals 0, while the right panel shows the spectrum for a mobile hole with tau equals 0.3 t. The results demonstrate the significance of the bond fermion basis in understanding the energy spectrum and optical properties of the Kitaev chain. The research paper investigates the energy spectra and absorption properties of a triple-dot nanowire system with a hole in the even subspace. Figure 4 illustrates the energy spectra as a function of electron-hole interaction V, for both localized and mobile holes. In the localized hole case, the spectrum exhibits 4 pairs of doubly degenerate states, corresponding to different dot states. The peak energies E0 and E plus or minus are identified and explained using equations 18a and 18b. For a mobile hole, the degenerate levels split into sets of triples, corresponding to the 3 propagating modes of the hole band. The mixing of states due to hole hopping leads to additional peaks in the absorption spectrum. The absorption spectrum is calculated using the polarization operator P, which creates an electron-hole pair with uniform probability along the nanowire. The operator P can be spatially resolved to create the electron-hole pair on a specific dot, allowing for detection of the optical signature of a Majorana Zero Mode, MZM. The absorption spectrum has even and odd parts, corresponding to each ground state. The authors derive an analytic result for the localized hole case, where the full Hamiltonian becomes block diagonal, and the subspaces of having the hole in each dot decouple. This leads to a simple expression for the absorption spectrum A, E, as a sum of contributions from each dot. The paper also explains the decomposition of an electron created at site I into a superposition of creation and annihilation operators of the 2 bond fermions on its 2 sides. This is depicted graphically in Figure 5 and expressed mathematically in equation B2. The interaction V-Na-in mixes the 2 bond fermions, leading to the observed absorption spectra. The research highlights the importance of spatially resolved absorption spectra in detecting the optical signature of MZMs. The author's approach provides a deeper understanding of the energy spectra and absorption properties of triple-dot nanowire systems, paving the way for further research in topological quantum computing and nanoscale devices. The research discusses the spatially resolved absorption spectrum for a chain of arbitrary length n, focusing on the role of bond fermions and hole mobility. For a localized hole, the spectrum features peaks at E0, E+, and E, with E+ being more prominent at higher V values due to its zero-mode contribution. This offers an advantage over scanning tunneling microscopy for detecting Majorana Zero Modes, MZM. For a mobile hole, the spectrum exhibits more peaks due to itinerant hole states and hopping hole mixing different subspaces. Figures 6 and 7 demonstrate these findings, showing the emergence of more peaks as hole mobility increases. The spatially resolved spectra highlight the localized nature of MZM and the leakage of zero modes from the ends of the chain as hole mobility increases. This research provides insights into the detection and characterization of MZM through absorption spectroscopy, emphasizing the importance of understanding the role of bond fermions and hole mobility in these systems. Here is a combined summary of pages 11 and 12 of the research paper. The authors present a theory of Majorana excitons, which are photo-excited conduction electron-valence band-hole pairs interacting with Majorana fermions in a Kitaev chain of semiconductor quantum dots embedded in a nanowire. Using exact diagonalisation techniques in Majorana and bond fermions, the authors compute the energy spectra of the system, confirming the existence of non-local bond fermions with zero energy. They introduce a valence band hole and describe its interaction with Majorana fermions, predicting interband absorption spectra and discussing the signature of Majorana Zero Modes in the absorption spectra. In the appendix, the authors provide detailed calculations for the exact diagonalisation of the Kitaev Hamiltonian for a chain of length 3. They present the matrix elements of the Hamiltonian in the even and odd subspaces, and then transform the Hamiltonian to the bond fermion basis. The authors also derive the analytic expression for the absorption spectrum of a localized hole, which is essential for understanding the interaction between the valence band hole and the Majorana fermions. The authors acknowledge the support of the quantum sensors and applied quantum computing challenge programs at the National Research Council of Canada, as well as NSERC Discovery Grant No. RGPIN 201905714 and the University of Ottawa Research Chair in Quantum Theory of Quantum Materials, Nanostructures and Devices. In the appendix, the authors use the exact diagonalisation technique to compute the energy spectra of the system. They present the matrix elements of the Kitaev Hamiltonian in the even and odd subspaces, and then transform the Hamiltonian to the bond fermion basis. The authors also derive the analytic expression for the absorption spectrum of a localized hole, which is essential for understanding the interaction between the valence band hole and the Majorana Fermions. The authors highlight the significance of their work, demonstrating the potential of hybrid nanowire semiconductor quantum dots, superconductor systems for the demonstration of Majorana Fermions. They hope that their preliminary work will motivate future theoretical and experimental research in this area. The research paper discusses the properties of quantum systems, particularly in the context of topological insulators. It begins by deriving the Hamiltonian for a specific system, focusing on the eigenstates and their energies. The authors then explore the behavior of the system under different conditions, including the effects of interactions and external fields. The paper also delves into the properties of the system's eigenstates, including their excitation energies and the role of symmetry in determining their behavior. Throughout, the authors draw on a range of references to support their arguments and provide a comprehensive overview of the subject.